In the last video, we were looking at the band diagrams of a Schottky diode. Now we want to understand how the current flows. And to understand how the current flows, we would like to compare a Schottky diode with a PN junction. More specifically, we will take the case of a P plus N junction, by which I mean that the P-type semiconductor is heavily doped. The reason we are comparing with P plus N is P plus is going to have a high concentration of holes. It sort of mimics a metal. You could think of a highly doped semiconductor as a pseudo metal, right? So that will be a more appropriate comparison rather than a simple PN junction, with comparable doping. Okay. So when you have a P plus N junction, we have seen this in the past that you have a large number of holes here compared to the electrons in the N type. So the hole diffusion is going to be dominant, right? Dominant current compared to the electron injection, right? So holes are going to get injected. So what controls the current in the external circuit? It's the minority carrier injection. Once the minority carriers are injected, they have to recombine with an electron in the N-type semiconductor. Okay, and then only that electron will flow in the external circuit, right? We saw that the minority carrier concentration was decaying exponentially away from the junction. So this minority carrier recombination is going to be the determinant factor for the current in a PN junction. What happens in a Schottky diode? So, well, we have seen that you have this sort of a picture wherein you have a barrier, electrons are going to see a barrier, and then there is a EF of metal here, right? So now, when will the current flow? Current flows when the electron is able to escape from this, right? When it is able to cross this barrier and flow, right? So this sort of a mechanism is not minority carrier injection. It's actually electron injection, I would say, over a barrier. Okay. And this sort of a process is called as thermionic emission. Okay. Simply saying that electron is going to cross a barrier and go into the other side. Okay. So this is fundamentally different from what you see in a regular PN junction. And also, Schottky diode is a majority carrier device in a way. Okay. Why do we say this? The reason is there are going to be a finite number of minority carriers, but how will they move? Will they carry current? Well, to carry current, what should happen? Here, there is a field which is in this direction, right? So holes are going to move in this direction. There's going to be some contribution of this, but this is going to be much, much smaller in number compared to the electron injection over the barrier. Well, you might say it depends on the barrier height. Of course, it does actually. We will take a few examples and compute the barrier height, and we will see that it is reasonably small. In the case of a regular PN junction, we saw that the barrier heights were like 0.6, 0.5, 0.7, that sort of a range. We will see that the case of a Schottky barrier, it's much smaller. We'll take an example and do this. Okay. So essentially, the majority carrier injection over a barrier is going to play a dominant role. Okay. And what happens with bias? Let's say if you had a applied bias voltage, okay, when VA is greater than 0, well, the barrier is going to reduce, right? The barrier that, Schottky barrier, we called it, 5B0, right, is reduced. Okay. And current flows. So J increases, current density increases, right? If you have VA less than 0, 5B0 is increased and J reduces, or rather J J cannot be there. It's a kind of a constant current actually. Okay, there is some complication here. Okay, let me describe that. We are essentially talking about, this interface, right? You can think of it like a interface between a metal and a dielectric. Semiconductor is like a dielectric. It has a certain dielectric constant. Okay. So now the electrons that are present in the conduction band of a metal, right? There is an electron, let's say here. What will be the field? Okay. Well, what happens is in the presence of an metal is like a perfect mirror for electrons, I mean electric field, okay? So the behavior of an electron in this situation can be modeled in terms of what is known as the image charge. Okay, we can think of the metal as having an image. If you think of this as a charge Q, there will be a minus Q here, and there's going to be certain electric field. Okay, I don't know if you have seen this, but in electrostatics, we call this image charge theory. Okay, if not, it's okay. So essentially, since metal is having lots of electrons, and it's going to be difficult to describe that, right? How if you start calculating Coulomb's law, each electron and the electron in the dielectric, you have to calculate the forces and all that. It becomes complicated. So one of the ways to analyze this problem without doing all that is simply replace this metal by an image charge minus Q. Okay, replace metal by image charge minus Q. Okay. Anyway, it's not that important right now. What is important is then if you have just a plus Q and a minus Q, you know how the electric fields will be. Okay. And of course, there's a boundary condition that we have to satisfy. And the consequence of that is essentially there is going to be an electric field due to the image forces. Okay, that is a conclusion that I want you to draw from here. So because of the presence of a metal, that the charge experiences an additional image electric field. Okay, electric field. Additional electric field due to image charge effect. I'll say. You follow what I'm saying? There's basic because of the transfer, because of the doping density, right? You have the space charge. Because of that, there's an electric field. The band bending happens. But in addition to that, because the electron is in presence of a metal, we can describe that as replacing the metal and putting an image charge. And so there's going to be some electric field. And that electric field is going to interfere with your electric field due to the space charge. Okay. So effectively, there's going to be a difference in the barrier. For example, here, the barrier is shown as this black, right? But because of this metal, because of this image charge effect, your actual barrier might be something like this. Okay. Actual barrier due to image charge. Okay. So there's a lowering of the barrier because of the image charge effect here in this case. So this one we will represent as phi Bn. Okay. Actual Schottky barrier. In the last video, we have seen that the phi B0 is the difference in the work function and the electron affinity. That gave you the phi B0, which is theoretically the Schottky barrier height. But in reality, the barrier is going to be slightly lowered because of the image charge effect. And that one we call it the actual Schottky barrier. Okay. We will take a moment and actually compute this as well. Okay. So now, so in a way, if you apply voltage, the barrier is going to be reduced further. So there's going to be larger current. And if you increase it, again, the barrier is going to increase and then you have current. That there's no current that flows in effect. Okay. There's going to be some leakage current. So the actual computations of it, we won't do how the current, we won't derive an expression for current, but we'll simply show you the final answer. Okay. It turns out that for a Schottky diode, you have the same form of expression as a regular PN junction diode. There is a saturation current here. This is reverse saturation current. Okay. And the exponential behavior, that's common. So the forward bias, they look very similar. The IV characteristics look very similar. The only difference is that the barrier height is much lower here. Okay, typically in the 0.2, 0.3 range. Barrier height is smaller compared to typical PN junctions. PN diode. Okay. And what else? Well, the saturation current density expression is different from a regular PN junction. Here, there is something called as A star, which is known as effective Richardson constant. Okay, this is just a number you could say, and there is a temperature T square, and then there's an exponential and the barrier height. 5Bn is actual barrier height of a Schottky barrier height, actual Schottky barrier height. So the saturation current is going to be determined on the barrier height. If the barrier height is large, then your Schottky, the reverse bias current is going to be small. But if your barrier height is small, we'll see that this number is going to be can be large. Okay, so that is one aspect that we need to analyze. We will analyze that in a problem in the next couple of minutes. Before I get to that, let us also think about how the current changes. The current is basically J times, let's say Js exponential QA by KT minus 1, right? So this is your current. Now, how much voltage is required to make current 10 times J? I want to increase the current by 10 times. What is the voltage that would be required? Well, that's going to be Js, and let's say exponential QVA plus, I'll call it delta V by KT minus 1. So I need to increase my applied voltage by, let's say, delta V to increase the current tenfold. And how much is the delta V? I want to find out. Okay. If you solve this expression, what you'll get is, you can solve this. You can assume that this is going to be significant. This is going to be this term dominant, because we are already in the forward bias. We'll assume that we are actually doing it in the forward bias. Okay, so VA is above threshold. Okay, so that you can ignore the 1. You take the ratio. So essentially, what you get is exponential Q delta V divided by KT equal to 10. Okay. So if you do this, what you get is delta V equal to, of course, 2.3 times KT by Q. Okay. KT by Q is 25 milli electron volts, right? And this whole product is going to be 60 milli electron volts. Okay. So this is a very interesting number actually. Okay. It turns out that the various devices, right? If you take the non-idealities into account, you can actually put in this as, we can put in a non-ideality factor into your current, and we'll say put here N instead of, okay, with non-ideal, okay, I'll write it here, with non-ideality factor, let's say J is going to be Js exponential QV applied by NKT minus 1. So your delta V is going to become, N is in the denominator, N times 2.3 times 2.303 times KT by Q. Okay, so this number can be different for different situations. Typically, it's in the range of 1 to 2. Okay, so you are 1 to 1.5 or so. But this delta V that is required to cause 1 order change in the current is a very, very significant number. We will actually revisit this when we look at MOSFETs. But essentially, you require at least 60 millivolts. Okay, it can be experimentally, it can be 90 millivolts or so. So you need that much of voltage change to cause a change in 1 order of magnitude in the current. And that is typical for all situations where you have current flow over a barrier. Like wherever you have a barrier and you have current increasing, that same thing happens. Even in the PN junction, it happens. So we require about 100 millivolts, 60 to 100 millivolts to actually cause 1 decade increase in the current in the forward bias, not in the reverse bias, in the forward bias. Okay. So this is an interesting thing. I want you to just make note of it. We'll come back and we'll talk about the implications later on when we discuss MOSFETs. Okay. So now let's try to calculate a problem. Okay. So the problem is, again, example problem from the textbook, example 9.1. Please refer to the textbook if you have questions. So what essentially they're asking is, determine the theoretical barrier height. Okay, theoretical barrier height and built-in potential and all that. Okay, for a metal semiconductor junction, N-type silicon with some doping density is given to you. Okay, so to determine barrier height, the first thing we need is, let's try to put it here. Oh, let's say there is an EF of metal, and there's going to be some semiconductor. There's going to be some EF of semiconductor, right? So to determine this barrier height, we need to know the electron affinity and the work function, right? So the electron, we have to take a reference level. Let's call this as some reference level. So related to that, this is going to be your work function of a metal, and this distance is going to be your electron affinity for a semiconductor. Okay. So in this case, we are talking about tungsten and N-type silicon. Okay. So let's look up that. Just a minute. Go back to my first slide. So tungsten was 4.55 and electron affinity was 4.01, okay, for a silicon. So if I go back, this is 4.55 and this is 4.01. Okay, so the theoretical Schottky barrier height, right? We are not really doing any phi b naught. Okay, the theoretical height was 4.55. If you write out the expressions, it has to be phi m minus chi, that is 4.55 minus 4.01, so 0.54 volts. Okay. We're leaving it in the volts unit. Okay, so the interchangeability of volts and EV you should be familiar by now. Okay, all right. What is the built-in potential? So built-in potential is when it's N-type semiconductor. Let's say there is a barrier here. So what would happen is there's a EF, right? And then there's going to be, this is your metal, and then there's going to be band bending here, right? There's going to be barrier. So the built-in potential was, this is your built-in potential VBI, and we saw that this was phi b naught. Right? So the built-in potential VBI is simply phi b naught minus the distance between EC and EF. We need to find out that distance. Okay. So in this picture, I want to know what this distance is. This is your EC minus EF. Okay. I think we called it phi n also somewhere. This was phi n also, you can call it. So what is this distance? Well, I mean, if you want, you can look up the expressions and calculate this. I'm sort of more comfortable. I don't remember the NC number, so I'll calculate it related to EI. Okay, so I know that there is going to be EI here. So this is going to be EI, right? Sorry, this is EI. So what I'll do is phi n is going to be EG by 2 minus. I'll write out directly. You should convince yourself that this is right. KT by Q ln of 10 power 16 divided by 10 power 10, I would say. Okay. So this is 0.55 EV because silicon band gap is 1.1 EV. 1.1, yeah, so 0.55 minus, this is 6 times 26 millivolts. Okay, 25 if I take it as 25 times 6, 150, and there is going to be, so 60 is not 25, 60, right? 60 times 6, 36, 0.36, right? 0.36 EV. Okay, so if you do this, this is going to be turn out to be some, this is going to be not exactly 60 millivolts, slightly less than that. So this might be something like 0.2 EV. Okay, so the built-in potential is going to be, we'll go back and substitute this into built-in potential. So VBI is going to be phi b naught was 0.54 minus, let's say, 0.2 EV volts. But this is EV, but there's a Q here, so then I can just talk in terms of volts. Okay, so it's going to be now you know what it is, right? 0.34 volts is the built-in potential. Okay, so please verify this. Okay, I mean it's easily possible that there's a small algebraic mistake, or the numbers will be close enough, I think. Okay, and then you're also asked to calculate what is the maximum electric field. Well, if you want to calculate electric field, you need to know the width of the depletion region. The width of the depletion was square root of 2 epsilon silicon divided by QND times VBI. Okay, so substitute, calculate, verify your answers, make sure that you get it right. All right. So this is how the this is how the barrier potentials will be. This is the theoretical barrier potential. The actual one will be slightly different. Okay. Theoretically, we got only 0.54. I mean, it's never going to be this much as well. I mean, it's going to be smaller than this because the electric field will be lowered. There is an image electric field which will cause the barrier to be lowered. Okay. All right. Let's take one more problem. So here the question is to calculate reverse saturation current, ideal reverse saturation current. Okay. Well, yeah, it's going to be some deviation from this. Okay, in ideal case, the reverse saturation current is going to be flat. Okay, but in the real case, there's going to be barrier which is going to be affected by the electric field. So there is going to be some variation in the reverse saturation current. Okay, all right. Anyway, we ignore that. So there is a tungsten barrier on silicon, and they gave you the effective or measured barrier height as this. Okay, so this is good, and you are given some Richardson constant, which is A, and you are asked to calculate what is the ideal reverse saturation current. Well, this is a very straightforward question. You just have to plug in. So 114 ampere per Kelvin square times temperature is 300 Kelvin square. Okay, times exponential minus Q times VBN is 5BN is 0.67 divided by the denominator KT is 0.0256, right? So 25 and 650. So 4 into 6, 24 and 2 times or 3 times I would say, roughly. So this is going to be 114 into 300 square into exponential, let's say minus 26. Okay, minus 26, 27, something like that. Okay, so if you do that, what happens? This is going to be some number which is in 10 power minus 12, I think. Okay, you please verify. Okay, so the overall current, if you calculate this number for a Schottky barrier, it turns out to be something like 10 power minus 5 minus 6 to 10 power minus 6 amps per centimeter square. That's the main point I want to make here. Okay, the reason for the problem is only this, not actually to see how you calculate. We'll assume that you calculate. Now you're not in a school, right? We don't care about algebra so much. At least I don't care about algebra so much. I care about the concepts. So what this is telling you, you remember how much was the reverse saturation current in a diode, PN junction diode? J0 was approximately 10 power minus 12 amps per centimeter square in a PN junction. This is an important difference between the Schottky barrier and a PN junction. Okay, so Schottky barrier exhibits large reverse saturation current compared to PN junction. This is an important takeaway from here. And also remember, it is dependent strongly on 5BN. 5BN is experimentally measured quantity depending on the type of interface and any non-idealities in the interface. This 5BN can be different. Okay, 5BN can exhibit large variations because of the deposition tools and techniques and so on. Okay, because of that, the reverse saturation current is all over the place. It's actually something that we have to characterize very carefully, Schottky junction, whenever you're fabricating that. Okay, PN junctions are more, easily reproducible, but Schottky you have to be very, very careful. Of course, even Schottky junctions are produced and they can be modeled carefully. But for each production environment, you have to carefully model it and find out what it is. Okay. So this is how the current flows, and the main points that you have to take away from here is that you have the similar current voltage characteristics, but the threshold voltage is much smaller. You see, ideally it was 0.54, but actually when it turned, okay, I mean, it's in this case it's slightly different. So it depends on the material, actually, metal and semiconductor, what type of interface we are talking about, and it can be different. And the voltage generally is actually much smaller at which it turns on, and you have a large change in the current. In the reverse saturation, you have a large, large saturation current compared to the PN junction. Okay. So with that, I'll stop. In the next video, I just want to quickly discuss the difference between an ohmic contact and rectifying contact, because that's a very important thing. And then from there, we will carry on. All right. Thank you very much. I'll see you in the next video.